start by reflecting on a few trends, then frame a little bit the little work we've been doing with sensors, the sensor in particular that you guys are kindly wearing right now, and in the end zoom out again and reason on broader impact of computational social science, let's say social development in general. So in terms of trends, what's happening, and what we will see in the next months and years, no? You know this already, we will have more behavioral proxies. The single cool thing, if we are researchers about the digital revolution, is that we have devices, we have instrumented interactions with digital platforms, and as scientists we can use the records of these interactions as a first order material for our research. So the proliferation of digital devices, wearable devices, sensors, Internet of Things, it will create more and more proxies for specific behaviors, and this will be opportunities for research. We'll have larger and larger cohorts of people. Already, you know, there are efforts to have 10,000, 100,000 individuals tracked for their entire lifetime through digital means, and we'll be able, you know, to do natural experiments, A/B tests, to reason on outcomes. And this comes with ever-increasing temporal span. Life logging is no longer an alien word. The idea that, like, for people who are born these days, there will be a digital record of all their interactions with all of their digital platforms through their lifetimes, right? And this is unprecedented. Very fine granularity. More use of unstructured data. So far we've been using relatively structured data because it's simple. Tina yesterday was saying, I hate natural language, right? Because natural language is actually tough. But we are getting better and better at dealing with unstructured signals, speech, video, natural language. Bruno talked extensively about embeddings and a bunch of other signals actually that will allow us to track and understand things, even from unstructured data. And unstructured data will be generated in larger and larger amounts. And in general, you know, the theme, and I think the capability underpinning computational social science is really the fact that we have a closer and closer representation of physical reality in the digital form. No? So the distinction between online, offline, it's already blurred. I think we should stop saying, you know, online, offline. There are digital platforms, that is what happens in the physical world, and the two things track each other and influence each other. And here I come, you know, to the topic of this talk. The link between online and offline, between the digital and the physical, this is mediated by sensors. The phone that you have in your pocket already has got like 20 sensors measuring different type of things. And this linking will become more and more pervasive, more and more fine-grained. Two things are really key here, especially when you think about, when you think about this hype on big data. You hear big data at every, you know, second word, especially if you talk to people in the industry. But two things are kind of real. One is that we will see more and more so-called lateral use of data, by which I mean using data for scientific purposes, but using data that was not originally designed to inform scientific research. And this is a plus because you have this data. It's also a minus because it means that this data was not designed with an experiment in mind, with a specific scientific question in mind. It's not a hypothesis setting, hypothesis testing setting, right? We will see way more of this basically because we will have more digital platforms, more sensors measuring stuff, and this stuff will be there, and the temptation to use it will be just as strong, okay? Of course, this has to be done with care. And the second thing, and this is, again, you know, a challenge, right? A lot of value, a lot of knowledge, a lot of decision-making capabilities, they will come after the data is collected, which again, it's not really how we are used to reason as scientists, right? We like to design an experiment to answer a specific question, to collect the data we need for that question. And this is challenging this paradigm in a sense, right? We will, suddenly you have, you know, I don't know, Reddit, or you have Facebook, or you have Twitter, and the data is already there, and then you start to sieve through the data and slice and dice to try and answer a specific question. This is a challenge, right? Now, let's speak about sensors. Sensors have been around for a long time. They're not a new technology, but the idea of sensors on people, this is more recent. In terms of consumer products, it started about a decade ago. You might remember this. This was one of the first wearable devices by Nike. It was the simplest you could possibly design. It had just an accelerometer on board. Accelerometers are really dirt cheap. Today you can buy a 3D state-of-the-art accelerometer for probably like 10 cents from ST Microelectronics, for example. So this is a very simple product to design. And then, this started a wave of consumer products. You might remember this connected scale that you could configure to tweak your weight whenever you were stepping on the scale, whether you want it or not. It's like different question. And now, of course, you start having much more advanced products. No? The Apple Watch, which is starting to track physiological features like your heartbeat. You start to have earbuds that can sense your heart rate by looking basically at how much infrared radiation your ears are shining and the modulation of that over time. And you start to have more and more, clinical, physiological sensing devices attached to the phone. Your smartphone will really become a hub, especially medical application for collecting this type of information. And this type of information will be enriched with all of the context that the phone knows about you and your setting, right? And then going forward, we already start to see sensors that you can put on your skin to get a better coupling with your bloodstream and start sensing, for example, glucose levels in your bloodstream. As you imagine, this is important if you are a patient suffering from diabetes or if you have any other of these chronic conditions. And already there have been experiments on ingestible sensors that you can swallow, and they travel in your digestive tract, and they talk through radio to a patch on your skin, which then uploads the data to your phone. Okay, this is arriving, and as you imagine, again, for clinical purposes, for medical purposes, this would be a game changer. Don't ask me why there is a cat here. This is designed for humans, but probably the paradigm that the cat should be there every few slides. This could be respected. So, like this capability of like fine-grained sensor-based measurement at scale is really unprecedented. And one of the cool examples that I always like to show is this one by Jawbone. Jawbone is one of the companies manufacturing activity trackers. Unfortunately, it seems they are going down as we speak as a company. But what they did here was to plot the fraction of people that are awake according to the reading of the accelerometers at a given point in time during one specific night. And this night was the night of the last strong earthquake in the Silicon Valley. And what you see here basically, is the fraction of people of these large cohorts. We are speaking millions of people in this case. And you see this is California, so it's kind of boring. People go to bed early. By 11 p.m. everybody is pretty much to sleep. And then at around 3 p.m. the quake hits. And you see that people who are in the Napa Valley where they make wine in Berkeley, almost 80% of the people wake up. And then they try to go back to sleep, but morning is arriving. Again, this is California, you start early. And so people go, well, they become active. And also what you see here is that as you move south in the valley, you see this is San Francisco. And this is down in Sacramento, San Jose, down to Modesto where they grow oranges. And you see that these guys didn't feel it. And you see that like this wake up behavior is dampened the farther away you get from the epicenter of the group. Right? So this is just a very simple example, but it shows you that we start to be able to have basically population scale physiological sensing or behavioral sensing of specific behaviors. And now if you move to something more recent and more serious scientifically, there is this very interesting article that you might have seen by Tim Althoff, Eric Horowitz and collaborators at Microsoft Research. What they do is that they combine sleep monitoring to an activity tracker by Microsoft with a notion of your cognitive performance or cognitive impairment measured by a simple proxy, which is how many mistakes you make when you type in the search bar of the search engine. And what they're able to do in this paper, which is really groundbreaking in terms of paradigm, is really to relate cognitive impairment, basically people sleepy, people feeling sleepy, at the population scale with sleeping patterns and disruption of sleeping patterns. Okay? So this is really a fusion of physiological data sensed by means of a wearable device and behavioral data, which is a proxy for cognitive impairment. And they find very interesting things, by the way. So this is just to give you a sense of the shape of things to come, right? We'll have more and more data layers that inform different behaviors, and we will be able to answer new questions or to give new answers to old questions. So the work I will be speaking about, which is closer to my own activity, took the move for very simple behaviors and very simple sensors. We started doing this like about 10 years ago, and what we wanted to focus was really behavior of people in physical space where the behavior is close range proximity. So the idea was to measure social networks at the scale of the meters and the seconds, in a sense, and to probe that space for a number of reasons. Basic human mobility modeling questions, computational epidemiology, social science and health, organizational science. As you know, there has been pioneering work at MIT in the group of Santi Pentland on reasoning about the performance of organizations on the basis of sensed social networks. And this type of data are not new. People have been seeking this data for a long time. This is, for example, a contact survey by the University of Warwick, which is meant to inform studies of epidemiology, mostly. And what you see here is that each individual is asked to list the names of people that they have met, whether there was physical contact, for how long they were in contact. And you can also, sort of be a spy and report an adjacency matrix for your friends. So you can list a bunch of friends here, and then this is basically the adjacency matrix, and you tick whenever you have reported, you have seen with your eyes the contact, right? As you imagine, this is simple, so you can do it even in very low-tech settings. It's also very difficult to scale, and it's subjected to cognitive biases due to how people recall contacts, right? So people early on started to use sensors for this. It was fun to discover actually that one of the first experiments in this sense was really near my hometown of Torino. This was by Olivetti, a company that was a pioneer in the digital revolution and then went down very early in the best Italian tradition. And what they were doing, they were using this very bulky device and were using ultrasound waves to actually sense the proximity of these devices and reporting information via radio to this other bulky object, right? And then of course, like this was back, 30 years ago, basically. And then you might know like a single pioneering study in this case, which was the reality mining project led by Professor Sandy Pentland at the MIT Media Lab, where they started using in 2003 sociometers, so devices that you could wear in your chest and would monitor a host of different signals. So your movement patterns, close range proximity, the tone of your voice, there is a microphone in here. The thing is that you cannot have everything, especially if you are in 2000, and so you have to choose whether you want scale or you want rich signals, right? In this case, the choice was rich signals. When we started working on this, we actually went for scale. So we really wanted to find out what was the simplest possible device we could produce and use to measure just one thing, and the one thing was physical proximity in space of people at the largest possible scale in the toughest possible environments. Okay, you often don't have the luxury of having Wi-Fi power. I will show you a few examples. So this is actually the device that you're wearing right now. It's produced by a couple of cool German folks, Milos and Britta Meria, who are now in Cambridge, and it was just a beacon. So it was just a little radio screaming out its name in the microwave spectrum. This is a very nice radio band to work with because it's free for open scientific use everywhere in the world except Japan. So if you're in Japan, sorry, you're out of luck. We never understood why the Japanese don't like this radio frequency. But this device was just a beacon. So it was just announcing its presence, and you are supposed to have antennas in the environment to triangulate the position of the signal. And this is tough to do, right? So what we did back then, thanks to early support actually from Professor Alessandro Vespignani, who is in the room, I went to Alessandro and I was like, we want to do this, and Alessandro, well, give it a shot. and was to get a bunch of these devices, test them. They didn't really work well because triangulation was very tough. So what we did was to modify them. We actually went in and modified the software running here, which is tricky because we have 128 bytes of memory, 128. Okay, so you're very constrained in terms of resources. And we modified these devices so that instead of announcing their name to an antenna, they would talk to each other. So we decided to go for detecting close range proximity. We would use an ultra low power radio signal that could only be exchanged between the devices if the devices were close enough. And so the devices work like this. You put a device like you guys are wearing on the chest of a person, and if the two guys are separated enough, nothing happens because there is no radio propagation of this ultra low power signal. You're only shining a radiation cone right now in front of you because the radio frequency we are using is in the microwave spectrum. It's blocked very effectively by the water in your body. So you're only shining radiation forward, propagation backward is 0, which is a good proxy, create an isotope in the radio signal, and it creates a good proxy for face-to-face proximity in a sense. And then when two people are close enough, what happens is that these two devices talk to each other, and then one of them, or both of them, depending on the situation, then on a different radio channel, it screams out not its name, but the fact that a contact between those two guys occurred. And those are the antennas, basically, that you see there next to Nicola. And then, of course, you have a computer system that records this information. So very simple. And this is what a conference looks like. This was ACM Hypertext, which we organized in 2009 at ISI Foundation. You see, it's a situation such as this. People in a room, they are not chatting with each other, they're facing the speakers. Every dot is a person, two dots are connected, these two guys are in face-to-face proximity. And then what happens is that the talk ends and people start interacting, and of course, they eventually go to the bar because this is a conference. In this case, you see that we are linking a lot of other information. You see there are avatars from, like pictures from Facebook. We have a lot of other information. I'll tell you a bit more about this later on. So this is just to tell you, what we are measuring and how, in very simple terms, we are measuring it. This is just one of many, many, many different efforts in this direction. I already mentioned the MIT Reality Mining Project, but there are people who used early on Bluetooth on board smartphones. There was an entire EU project using modes in hospital settings, pioneering work by Marcel Salaté at Penn State University, measuring interactions in school. Many of you are familiar with the work of Sune Lehmann at BTU using smartphones in a cohort of students, and so on and so forth. Right now there are like many sociometric studies at different scales going on. So this is good because it means, it's not just about what I'm telling you about. This is a wave of like sensing capabilities that's mounting, and the signals will be there and are there to stay. Our specific goal there was that we wanted large-scale, time-resolved, so high-resolution, close-range proximity networks across a variety of settings. So, I'm a physicist by training, and I don't want to see one picture. I want to see a million pictures and try to see what is stable across pictures and what generalizes to other settings and what doesn't, right? So we've been doing this for the last 8 years, pretty much all over the world, partnered up with a large number of institutions. And the logic for doing this over and over and over was really to understand what are the statistical features that are robust, what the data tell us that we didn't expect from theoretical principles to start with, and what's the relation between things we knew from theory and reality and vice versa. So this was a long and still ongoing effort. It involved re-engineering this device several times. Many of them didn't work. These guys never actually worked, not even once. And then we started, scaling up because we started having more robust hardware, more understood behaviors. So we tested at the conference, which was aptly named Nothing to Hide in 2008 in Berlin. This is organized by the Chaos Computer Club. Some of you might, especially the guys from Germany, might know it. It was a great occasion to get the system basically attacked at the radio level, at the firmware level. This is the largest hacker conference in Germany, and so by definition, whatever you bring, whatever device you bring there will be attacked. which was great because we came out of this with a very strong hard encryption of the transmission between the devices with robustness to a subtle attacks. People were recording our radio signal and playing it back at us at different powers, so a lot of devices would be messed up by this, right? So we learned a lot of failure modalities. Then we started to reason about integration of different types of signals. And this is a very early study that we published at the International Semantic Web Conference, where at the conference, we allowed people to link the ID of their device with their identity in Facebook. You can see that this is old from the social media that we were using. You see, okay, you have Facebook, but then this was Flickr, this was Delicious, which some of you might remember, but now it's long gone. This is Flickr, which, as you know, is going down as we speak, unfortunately. And then basically, we started reasoning about temporal networks, multiplex networks. You see, these are physical links, these are online links. This is a link actually which exists across all of these layers. And we also started to reflect, trying to push the envelope on how to respect people's privacy, on what type of services are okay to provide, how to obtain consent. In all of the data collections I will mention, we pretty much conform to a policy of pure opt-in. So in every single case I will be showing I have written record of consent from the person I'm tracking, or sort of a more blanket situation like in a hospital or a school, but there is an explicit consent. And then we started, playing tougher games, so interactive installations. This was done in 2009 with the Science Gallery in Dublin. And they were simulating sort of an epidemic at the Science Gallery. It was very dramatic in the way it was presented. And so we modified the onboard software to run an epidemic on top of the devices. The devices, when they were infected, they were blinking very, very hard. And if I was spending time in proximity of somebody infected, my device would become infected. So this is what happened. You see this guy here, gets in contact with this guy, and then bam, it becomes infected. Okay, so we started experimenting with this, and we also started to reason about how to properly visualize this type of data. This is a challenge. This is a very high-dimensional, very rich type of data set. This is, for example, something that was done by Wouter van den Breck, a designer who was involved in this early on. And what you see here is a face-to-face proximity network of people in a museum, in this case, at this infectious exhibition in Dublin. And what you have here is, again, an individual. A node is a person, two nodes are connected. Those two guys were in face-to-face proximity. The color codes the time at which those guy was first seen by the system. And you see this is like the hand of a clock. So it starts at noon. You can see the guided tours in the museum. You see this cluster of people coming in at the same time. Then they go out, another cluster comes in, but there are a few individuals who come in between, and they sort of connect these two structures. No? And what you see here is that this is the longest path in the contact network, which shows you that even in a situation such as a museum where you have a flow of people and nobody stays there really for a long time, there is still, if you have a high enough flow, a fully connected network of contacts. And then of course you can start reasoning on what generalizes and what doesn't, because we were doing this for 3 months. We monitored 30,000 people, and so we have one snapshot, time resolved of this contact network for every single day. And we started really reasoning in terms of statistics, right? Now, it's really key, and I really believe strongly that you're not doing science if you're not sharing the data. You need to allow a broader community to reason on this data. So we actually pushed hard and worked a lot on releasing every single data set we could, which means telling people beforehand we are going to release the data, you're comfortable with that. And then now, if you go here, you can find several different data sets of different type of proximity networks, mostly face-to-face proximity, school conferences, museum exhibitions. And these are post-processed, they're cleaned. These data, as they come, I will show you, they're pretty dirty. And so it's actually a good starting point. And it's really nice to see that people have been using it. I was checking a few days ago, there are now almost 400 articles using this type of data sets. So this is another good news for you guys. You're young, share your data, people will use it. And as you imagine, this was a very large collaboration network, so I don't have time to thank everybody here. Let me just thank Alain Barra, who together with me has been the PI and has been suffering on this project for almost the last 10 years. Okay, if any of you have questions at any time, interrupt me. I mean, I really enjoy it. So, are there any urgent questions on anything you've seen? Yes?
Just wondering, what about space? The small points are moving? Is there like because of the antenna that they...
Oh, yeah, you mean the kind of like the layout, really, the movement of points.
In the space.
Yeah. So in the visualization you've seen, we only have a loose spatialization of the data. So we use the antennas, as you say, as a proxy for presence of persons at specific locations. You can also use this to induce a co-location network, in a sense. But for the rest, we are just visualizing topology there. There is no spatial information. We are actually explicitly not going for indoor localization in the geometrical sense. Just because that's very complicated. Can be done, I will discuss that. Other quick questions? Okay. So now I want to show you a little bit how the data work, how the data look like. Okay? If we have this type of data source, so time varying, large scale graph, basically, how does this look in real world settings? And conferences are relatively easy, are also relatively artificial, so let me show you a few more important settings. We work quite a bit in hospitals. In hospital, people have been seeking this data to reason about nosocomial infections, to reason about optimizing specific outcomes at the level of the hospital, the shift of the nurses, stuff like that. And this is, for example, an hospital in Roma. This is a collaboration with Professor Tozzi of the largest children hospital in Italy. And what you see here is 1 week of data. I projected away time, so this is a static graph obtained by projecting away the temporal information. I only retained one little bit of temporal information in the edges. You see that the edges are colored, so the color of the edges codes for the stability of that link over time. So the orange links are very stable over time, whereas the cyan, the bluish edges, they're fluctuating a lot over the course of this week. This is a role structure population. People have well-defined roles that we know of. So you see there are nurses, they interact a lot with one another. You have doctors, they don't spend much time in the ward. They typically go in, interact, see a patient for a moment, interact with the nurses. But typically, this is the common chain, in a sense. So you have the doctors, you have the nurses, you see a lot of coordination, a lot of cohorting. The auxiliaries are typically receive orders and indications to help out the nurses. They don't interact much with the doctors. And then you see these three categories in a very fluctuating fashion interact with the network, with the sub-network of patients. This is a children's hospital and their parents. This is a world where they treat respiratory infections, so there is a policy of having only one parent per patient, only one parent per children. And so these edges that you see here, if you lay out properly the network, really code for the stable, strong relation between each children and the corresponding parent. Okay? So you see a lot of the organizational structure of an hospital exposed in this data, and then you can start asking more difficult questions, which is the stuff we've been dealing with in the last few years, which is, okay, now if we link this data, if we cross-mine this data with clinical and biological data in a hospital, can we understand something more about transmission in hospital setting of specific pathogens? Of course, pathogens for which close-range proximity is a proxy for transmission, so for example, flu. And I will not go into the detail, but this is just an example of the stuff you can do. This is an acute geriatric unit in Lyon. This is a collaboration with the group of Philippe Van Emsa. And what we did here was to measure the social network proximity for about 12 days. But simultaneously, what we were doing is that every morning we were putting a Q-tip in the nose of everybody, basically, and doing PCR amplification and virological confirmation of the mucus we would extract. And so here what you see is really the presence or lack of presence of a specific pathogen at a specific node as a function of time, biologically, clinically, and microbiologically assessed, together with a contact network. And you see that, of course, you cannot point your finger to transmission events because this is an open system and we are monitoring only a part of it. But you do have a few situations where you see strong contacts between an infected individual and a susceptible individual, and then that individual becomes infectious a few days later. So we can actually rank specific contacts as potentially at risk for transmission in that setting. And you can start reasoning on how to use this information to think about the spatial structure of the hospital, the cohorting of the nurses, and basically whatever you can do to reduce the probability of these high-risk contacts. Of course, this is very preliminary work, so I'm just showing it to give you a hint of where things are going, especially when we'll have more sensor, we'll have more clinical and microbiological data that we can link with behavioral data in these settings. Another setting which is important is schools. For a number of reasons, if you're reasoning about flu, because it is known that schools play an important role in the community transmission of flu. But at the more fundamental level, they're interesting because schools have a complex mesoscale network structure. You have kids moving around, but kids have to stay in class at specific times. There is an organizational rhythm to the school, and this imposes a very complex structure that you will not observe, for example, in the data we are collecting this day. No? I mean, right now we are here, but during coffee breaks you associate however you want, right? So that's the beauty of growing up. And this is how the data look like. This is a school with 10 classes, 5 grades. What you have here is that each circle is a class of the school, the dot at the center is the teacher. And you see that when this data collection starts, it's in the middle of the morning, classes are running. You see in some classes they have more social activities, lots of contacts. In other classes, probably this is a situation such as this. So you have few pairwise contacts, maybe of children chatting or nearby each other, but overall there is not much activity. And then, as time progresses, what happens is that lunchtime arrives, and all of these guys move to either the playground or the cafeteria, and so of course you have a completely different organization of the network popping up. Okay? And as you might imagine, this type of connectivity patterns, which entail strong correlation between different links, which do not entail a community structure, it's really correlated activity patterns of specific links due to organizational rhythm. These patterns have got a strong impact on epidemic processes, for example, on this data. You can tease out the activity schedule of the school from this data. You can see, for example, that these guys, they go have lunch while their friends are in the playground, and then they swap, and then they go back. Some classes you lose them because they go play outside, and then they appear back, and so on and so forth. So it's really complex to work with this data, and I just want to give you an idea of like how rich it is, but also how complex it is and how dirty it is in a sense, right? Because you're capturing a lot of heterogeneities that are not really core maybe to the process you want to study, that are really specific to the schedule of that particular school at that particular time, right? Of course, as you project away information, you start to have more generalizable knowledge, and you start to understand better things. So, for example, we project away time, and this is the same data. Right now, this is a static graph obtained by projected away time. And what you see here, for example, is that children, when they're very young, they mix irrespectively of gender, but as they age, you see what happens. You start to have the boys and the girls who are sort of segregated. This is before puberty, okay? So children sort of segregating, and then of course, if you study high schools, you see the opposite phenomenon. And the reason I'm showing this is because this starts to give you an idea that you can ask new questions with this type of data, and you can see finer phenomena. I'll show you just a couple of examples. Some things are simple. For example, of course there is grade homophily. Of course there is class level homophily. You can project away individuals. In this matrix, what you see is just how many contacts you have between children of this class and children of that class. And you see there is this diagonal structure, which is basically grade homophily. People of class 2A tend to hang out with people of the same age of class 2B, in a sense. This is due both to probably age-dependent homophily, but also due to the organizational structure. These guys are forced to be in the same space at the same time. And you have other structure which arise purely out of organizational structure. You see this brighter box here is actually due to the fact that these classes have social activities together. They're the younger kids. But then you can start asking finer questions. For example, I mentioned homophily now, and here you might have an hint that there is age-dependent gender homophily, and we may want to study this. As it turns out, there are hundreds of articles on this topic, but based on very traditional data, so without the possibility of measuring individual interactions, and the strength of interaction in particular, as measured by how much time I invest in face-to-face proximity with Andrea, for example, right? So what we did was the simple stuff. You can take a node and you can compute for every node very simple indicators of gender homophily. So you can take the ego network of the person and see what fraction of their alters have the same gender as ego. Okay? So this is the same gender individual preference index, in a sense. Very simple, very established. If you speak about this, people in social sciences will understand the language. And then you can ask simple questions, like, is there homophily? And of course, yes, there is. It's statistically very strongly significant. Does it evolve with age? Again, yes, very strong statistical support for this in this setting. But then you can start asking really tough questions that are very difficult to answer with traditional data, like, does homophily behavior depend on gender? Are there differences between how males and females exhibit homophilous behaviors as they age? Does homophilia depend on tie strengths? If I disaggregate all of my data in terms of weak ties and strong ties, behaviorally defines as how much time I spend in proximity of somebody, can I see a pattern? And the answer is really complex. This is, for example, a picture of like age-dependent gender homophily in a primary school. Of course, limited to this primary school in this specific setting. And I need to explain this a bit because there is a lot of information here. What you have on the y-axis is the person correlation coefficient between age of the kids and the same gender preference index. So it's positive if gender homophily becomes stronger as children age. And it is negative if it becomes weaker as children age. What you have on the x-axis is a threshold on the strength of a tie. So if I am at 10 minutes, I am only retaining in the analysis links that correspond to more than 10 minutes of face-to-face proximity. Okay? So if I only spend with Andrea 5 minutes over the entire week chatting, that link will not show here. Okay? So as I move to the right, I'm filtering through a backbone of strong interactions. Okay? And only those. Whereas as I move to the left, and I get to 0 ideally, I keep all of the interactions. Okay? So here I have the weak ties and the strong ties. Here I only have the strong ties. And then you see what happens. What happens is, it is rather nuanced, and this is something actually that we are able to find a few references in the literature about this phenomenon possibly be there if one could only look. So we actually went there and looked, and the phenomenon sure enough was there. What you see here is that for boys, the picture is simple. Boys, as they grow, they just develop stronger homophily for other boys, regardless of tie strengths. Okay? For females, you see the picture is more nuanced. For strong ties, you see this correlation coefficient is positive, which means that for strong ties, you have increasing gender homophily. Girls, as they age, they develop strong ties, preferentially more with girls. But you see what happens if you include the weak ties is that this actually crosses over to negative. And the way you explain this is that basically this is a subtle difference in the way boys and girls arbitrate their time. Whereas boys, as they age, they invest more and more time, both for the strong and weak ties with other boys. Girls, what they do is that they focus the strong ties more and more on other girls, but the weak ties on the boys. So you really see how people, our children in this case, as they develop, they arbitrate their time in a different way. Okay? And this is something, of course, that you can only see and understand if you have access to the possibility of filtering by tie strength, behaviorally defined as face-to-face proximity. Okay? So this is just one simple example, and then you can do more sophisticated things. For example, you can this is something which we have done with the Berkeley School of Public Health. What we did here was to relate in school settings during lunch traditionally measured indicators of depression and self-esteem with the network structure. So every month we were collecting 3 days of data, we were aggregating them, and we had one picture every month. And then in each of these situations, we would collect also standard questionnaire-based measures of depression and self-esteem. And I will not show you the number, but basically what we found is that for girls, depressive symptoms are associated with social isolation in the network, but for boys, this is not the case, for example. And again, this is a nuanced distinction, which you can only make if you have this type of data. Okay? Other questions on this? Okay. So let me skip this because I'm going slower than I thought, so I will just spare you some boring stuff. Let me tell you instead another couple of things. The first one is that this is one specific proxy, and it's also new, so we don't know a lot about this. So what is the relation between these proxies and other more established measures of other established ways of measuring social networks in physical space, right? And this is something we have experimented a bit, and I'll show you just two examples. The first one was in collaboration with Gabriel Lew in Hong Kong. This was a large school, 1,000 people, 1,000 students for about a week. And in this case, what we did was to relate the social network from the sensors with the social network obtained by video. So we put video in specific settings, in specific classes of the schools. They actually painted, you see, on the floor a grid that would aid some poor students who actually annotated by hand close range proximity frame by frame for several hours in this class. Okay? And this was supposed to be a sort of validation of our method. And then what did we discover? Actually, we discovered that different annotators of the image disagree with each other more than each of them disagrees with the sensors. So what we discovered out of this was actually a negative result, that what we thought was a ground truth is actually a pretty bad kind of signal, right? It's highly inconsistent, it's very dependent on the annotator. So this is a classic negative result, and then we were unable to publish because it's really negative. We discovered that the ground truth is not really like what we thought. But this is important to reason about. Like, do not get stuck on thinking that the traditional notion of ground truth that you think describes the phenomena is actually a good one. We need to challenge that, especially when we start to have these type of signals. And then the other thing we did, and this was in collaboration with people at Public Health England, with Timo Smiszek in particular, was to actually, at a conference setting like this, to use contact diaries, such as the one I showed you at the beginning, where people report their contacts, and the sensors. And we compare them. This is not the single study where we did it. We had like 3-4 studies on this, but this is one of the cleanest, we think. And what we found here is what you expect, that people will remember about the long contacts. So if you focus on specific contacts, you see that 94% of those that lasted more than 1 hour, you find them in the diary. But of course, as you go to weaker and weaker contacts, you find a smaller and smaller fraction of them in the self-reported information. So you really see a recall bias in the diaries, which you don't have in the sensor data, of course. But at the same time, what we found is that if you consider the two sets of contacts, those from the sensors and those from the diaries, neither is a subset of the other. And this really tells you a cautionary piece of information, which is do not trust even the sensors entirely in the sense. They have their own biases and noises. This is just another proxy, and we have to learn its power and limitations as well. And then let me just reason a bit on the type of network structures that you find in this scale. We have seen that in some of these settings, you have role classes. In the hospital, you have the different, patient, nurse, doctor, auxiliary. In the school, you have classes that are the basic organizational building block. In the general case, you don't know what the classes are. And then you can cast this as an unsupervised machine learning problem. You can try and have the data tell you what are the behavioral equivalent classes of nodes, which is a way to if you want to reduce the dimensionality of the data, reason about the patterns that are there. And yesterday, actually the day before yesterday, Bruno talked extensively about dimensionality reduction based on matrix and tensor decompositions. And here I show you just one example based on tensor decomposition. The basic idea is that you take this time-varying graph, this multi-layer network where the layers are different times, and you pack it up in a three-dimensional matrix where you have basically that each frontal slice encodes for the adjacency matrix at a given time. And then what you can do is that you can use very, very well-known methods and algorithms to represent this data as a superposition, as an additive superposition of linear terms, where each term is the outer product of three vectors. Actually, there is a theorem, relatively recent, 1999, due to Kruskal, that tells you that you can always mathematically represent an object like this as a sum of rank 1 tensors, but this rank might be high. And this provides you with an avenue for dimensionality reduction because you might impose a lower, reduced rank on the data. And so what you do is that you take the original data and you try to approximate it with the sum of a given number of rank 1 subnetworks, which yields a minimization problem of this kind. This is the original data, and this is, you see, a sum over a chosen reduced dimensionality of the outer products of three vectors. And there is a latent component, which is really the number of mesostructures, number of subnetworks that you want to extract. Of course, you have if you have an undirected graph, you have a symmetry. So a couple of these terms actually can be identified. And basically, this boils down to extracting two objects, the A's and the C's. You can extract basically two matrices out of this. One is a matrix that associates the latent components you're extracting, these are R, with specific groups of nodes. And the other associates those same components with an activity pattern over time. And so you can tease out simultaneously, if you want, the group structure, the community structure, but they're not really cohesive communities. They're really group of nodes with homogeneous temporal behavior, in a sense. And if you do this on the network data that I showed you, you find something like this. These are like 14 components in this case, so this is a rank 14 dimensionality reduction of the data. And what you see is that you can recover all of the classes. Here the nodes are ordered by class ID, so these structures emerge naturally as the classes, but the algorithm, of course, doesn't know about the existence of the classes. And you see that for classes, you have activity patterns that are consistent with classes. No? They spike in the morning and the afternoon, and they're silent at lunchtime over the 2 days. Okay? So this is the component node matrix. This is the component time matrix. Okay? But then you see that you have some of the activity patterns, some of the subnetworks. They mix nodes from different classes. You see this one mixes 1A, 2A, 2B, 5B, 3B, and you see that they are temporally localized. And this corresponds to the lunch break of the second day. This is the playground break of the second day, lunch break of the first day. So basically you have a method, and you can devise several others, and you shouldn't marry this one in particular. But this shows you that techniques that we know from unsupervised machine learning and dimensionality reduction allow you to expose mesoscale structure and subnetworks in this high-dimensional data that correspond to specific activity patterns, specific organizational rhythms. And of course, you can validate this with the metadata you have. One big question here, which is the single reason why you do structure detection in networks, right? You don't do structure detection to find structures, but you want to ask typically a question, which structure is important for what? So imagine that you have a dynamical process on the network like an epidemic process, and you want to understand which of these structures is now most responsible for epidemic spreading with given parameters on this network. And the cool thing of having an additive representation, such as the one I showed you, is that you can use it to unmount the network and remount it by removing specific mesostructures. So one thing you can do, for example, is you can take the original data, you pack it up in a adjacency tensor, you do the decomposition, and then you decide, okay, let's remove the lunch break. And you can just kill it. So you zero out those elements in the dimensionality redacted representation. You pack it up again as a tensor, and this is again a diminished network. This is a network from which you remove selectively a specific correlated activity pattern. Like this is the same guy as this, but without lunch on the second day, in a sense. And then of course you can simulate an epidemic process on the two and compare them, right? And you discover, for example, in the school case, that this is a delay ratio of the epidemic, how much you delay an epidemic as a function of which component you're killing. And you see that big structures such as classes, they don't, if you remove them, nothing much happens in terms of epidemic delay. But this light structure that link different classes, so these are sort of mesoscale weak ties, right? They're not weak ties themselves, it's a set of links at the mesoscale level that couple classes globally, right? And these things, if you remove them, they delay significantly an epidemic. So they have a strong impact on propagation, right? And let me show you another example of these decompositions. This data, as I told you, is very dirty, normally. We discovered this the hard way in the Hong Kong school that I mentioned. So what we were doing there, we had 1,000 sensors on the ground, and the school managers didn't want the kids to bring the sensor home because they thought they would lose them. And so they asked the kids to leave the sensors on the desks when the class was over, which was a disaster for us, as you imagine, because what happened is that you see a lot of spurious contacts between the sensors, now suddenly, in the same drawer or on the same surface. And naively, initially, we thought we could use the school schedule to clean data, to just, like zero out specific areas in the data. Here, what you see is like how many contacts you, sorry, this is time, and this is the classes, and the color scale is how many contacts you have in that specific class at that specific time, right? And you see that you have a lot of activity during the weekend, a lot of activity during the night. The school classes are just these structures here. You see that there is some heterogeneity, but you see that during the night you have these frozen accidents, these frozen proximity patterns, but very strong due to spurious contacts related to sensors being abandoned, in a sense, right? As it turns out, the school didn't have a record of the reliable record of the class schedule, so we couldn't use those to clean the data. Doing it manually at this scale is a disaster because this was like about 10 billion rows of data, and so we actually resorted to this low dimensionality decomposition method. Basically, we have a machine learning algorithm that uses non-negative tensor factorization to decompose this network, tag each component as spurious or genuine, and remove selectively the spurious components. And so automatically we were able to clean the data. Basically, you see that here during the weekend now you have absolutely zero activity, the nights are clear, and so this is just to tell you that we will see in the future, I think, more and more machine learning, more and more AI to actually work on this sensor data and remove a lot of the dirty stuff that this sensor are capturing. Questions on this? And let me move. Yeah, I was here. If not, I'll show you what's going to happen in the future. Okay? I'll ask for like 2-3 more minutes of your attention.
I have a
yes.
Quick go back to the. Oh, can I yell? Thank you. All right. No, so if you could go back to the tensor decomposition, it's quite interesting that. Yeah, forward. A little bit.
This one?
No, the next. So when you remove.
Or the data cleaning stuff.
Yeah. So it's interesting. No, not the data cleaning. The next slide, I think. Yeah, this one.
Okay.
So it's interesting that there are some components that mix some of the groups, like classrooms, but they are not as useful in deterring the infection.
Oh, that's due to, thanks for this. Here we are simulating a very simple process, an SI process. This component temporally happens after this. And so the process is
Oh,
pretty much
I see,
over.
I see,
If you do this properly, like an SIR or something more realistic, then of course you get a different picture.
Okay.
But thanks for spotting that. I mean, good catch. So let me show you. I want to close by telling you two things. The first one is what are the challenging, the some lessons learned, and the second one is where these things are going to move in the near future. So in terms of challenges, the biggest one is really logistics. You wouldn't expect that. It's not the sensors. It's like the mechanics of giving out the sensor, recollecting them, handling the metadata. Just imagine that you have to package things differently according to the setting, right? In a hospital, we needed to package the sensors in a way it could be sterilized. In a different hospital, this wasn't viable because they were using a different sterilization mechanism, and we had to come up with something like this. In Africa, and I'll show you some example, we are working in developing settings, we needed to conform with local aesthetics because people would find this scary and ugly and throw it away, right? So this is a lot of the work that goes into carrying out measurements like this. So it's really almost ethnographic. Actually, it's genuinely ethnographic work in some cases. Engagement is also a big issue. As I told you, we stick to a pure opt-in policy. So actually, we obtaining consent to people, actually informing them is really a lot of your work. Metadata collection and handling is a nightmare usually, and in the end we resorted to basically 3 levels of IDs. We have an ID system for the persons, an ID system for the devices, and an ID system for the radio, so that we can handle, for example, replacing a damaged sensor or correcting swaps, accidental swap of sensors, damaged devices for which we replace the hardware. You know, this is okay at this scale, but if you're dealing with tens or with hundreds of thousands of devices, all of the corner cases will happen in our experience, and you will spend 90% of your time dealing with the corner cases. So you need to plan ahead. Data quality and data cleanliness, I saw you, is an issue. Validation is another issue, mostly because you typically need to convince somebody from a different community that the signal you're getting is actually usable. But your signal, as I showed you, in some cases challenges the status quo in terms of ground truth, and so this becomes also a challenge in getting your message through. And the other thing is that hardware is a moving target. Unfortunately, whenever you, for example, the devices that you're wearing, we cannot manufacture them any longer. The CPU that they have is no longer on the market. And you know, like, and this points to something that we are discussing a few years ago. A few years ago, at some point, we were like, well, you know, in the future, we'll be using smartphones anyway. And now 10 years have passed, and we are still not using smartphones. Why? And the reason is simple. The reason is that, whereas because of Moore's law, the cost of measuring just proximity is going down very fast, what's happening here is, because of Moore's law, is that people are adding more features. So in a sense, the cost of this is not coming down as fast as the cost of the burst sensor. So actually, if you ask me at this point, I don't believe that smartphones are really the future unless you have specific contexts where you know you can deploy them, such as the studies by Professor Lemon, of course. But in many settings, and I will show you a few ones, I think we'll see more and more sensors before we see less. And this is also tied, you know, to what people call the IoT, the Internet of Things revolution. And the other challenge is that as you know, in computational social science, typically we piggyback a variety of signals and data sources. Some of this data is just out there. Social media data, we are using with social media data, with Twitter, just because it's there, right? Not because we like Twitter. We have a question, and Twitter data there. So, yeah, another Twitterology paper, right? Then there is, you know, a space of like volunteer data where you actually ask people to provide data. You have participatory systems, you know, like web-based, flu survey and stuff like that. You have different modalities of interaction of users, right? Here the user is aware and contributes to data collection. Here the user is passive. So in a sense, in the social media data, you're spanning the two. In participatory system, the user has to be active, so you need to convince this guy that he or she wants to donate their data. But a lot of the signals that we will be working with are in this space of proprietary data passively collected. If you think of Internet of Things, you think of products that will be connected, but will be not operated by you. and the data will be not collected by you, and you will want a scientist to work more and more on this data. Think of an example of search engine queries, Google Flu Trends. This is a classic example of a proprietary, passively connected data source. So the challenge we'll have as a community is really to understand how to access this sector of the data, and also what this means ethically, right? Because this data come with specific business goals attached. So how can we make ourselves relevant enough that these companies will want to share our data? How we ensure that we are using the data and our methods for the best interest of the users who are providing these data points? This is really a challenge, right? So right now, basically what we decided to do is keep sticking with sensors. After all, we've been working with them 8 years, might as well be 10. But the new settings where we are working are really challenging. We are really starting to work in sub-Saharan African settings, in developing settings, where not only a smartphone is not viable, but you don't have power, you don't have network connectivity. So what we did was to engineer a new device, and the new device basically has got an onboard memory storage, accelerometers to understand whether it's been abandoned, and for the rest works like the old one. If two devices are close enough, they lock an event, a proximity event, locally on the device. There are no longer antennas, and basically we can work now freely in contexts where normally it would be impossible to work. We started testing this in controlled but rather wild settings, military exercises of response to an emergency. This is in collaboration with the cremating master in disaster medicine. What they simulate is a crash of a plane on the ground in this case, and the response, the emergency response to that. And this specific case involved, like 20 ambulances, 500 people on the ground, a field hospital, and we put sensors on everything. Basically, this was really a challenge. Like, can we operate in an environment like this? What can we learn by operating in an environment like this? How does the system fail? And so we instrumented, you see, everything. This is the field hospital, and in this case, this is a real Internet of Things scenario. Here you have sensors on people, on medical instruments, in hospital rooms, on the ambulances, and you can really see in real time or retrospectively, depending on whether you have an antenna or not, who is in contact with what, how the patients flow, what's happening on the ground, and so on and so forth. So this was useful for the disaster response exercise manager to understand and answer some specific questions, mostly about patient flow, and it was useful to us to understand how to push the system forward. For example, this is what happens to a patient. You see the patient initially is in the field. You see you have contact with the first doctor, the first responder who gets to see and triage this patient, and then the ambulance arrives and you have contact with the ambulance staff, and then you get into the hospital and you start interacting with the rest of the hospital. So right now we are doing organizational science studies and performance analytics on top of these data in hospitals. We tested things in households. Again, here data are tough to collect because you cannot go inside the home of people and start putting antennas. We partner up with a few hospitals which actually give patients sensors, and the sensors are brought home and then they're given back, and then we see what's in the data, and we are starting to learn a lot of nuances in these mini family networks in households, right? And I will close by just showing you what we are doing now in Africa. This is mostly in Kenya and in Chad. It's in collaboration with Wellcome Trust. And what we did here was really to engage people on the ground, train them on the ground. Initially we ran a pilot a couple of years back in 5 villages in rural Kenya, just to see whether we could operate there, right? What was viable, what kind of sensor packaging we could use in these settings, the quality of the data. This is in collaboration with the group of James Knox, Moses Kitty. Some of you know him. He's a PhD student who has been active on the ground to run this. And we started seeing, you can collect the data, you can compute like contact matrices broken down by age, which is the thing that really epidemiologists want in these settings. And when we were confident enough, we started scaling out. So right now we have an experiment that just completed. This was 1,000 individuals tracked mostly both in rural Kenya and in urban settings. So two very different social structures. In the cities you have the traditional nuclear family structure, but in the rural setting, this is a village, you see down here. You have multi-generational extended families living in households, so a completely different social network structure at the household level. And we wanted to understand how to better model this context, how to relate what is different and what is stable across this context. And to work in this context, you really need to do a lot of work on the ground. This is my collaborator Moses, has been leading the work. You need to create awareness campaigns to explain people what this is, why it's important to do it, to buy in the consent for the specific tribes, especially in rural settings, that are responsible for managing the life. And then there is the complexity of dealing with the sensors, right? You see here we have we start to order 1,000 sensors, and you see this is the tough job. You issue them. Uptake in this case was only 46%. You get back only fraction. Some of them are damaged, some of them are corrupt. Then we randomize, we choose random sample of students, index cases, and we instrument those students and their households. And so this is the household branch, this is the school branch, and then we put together the data. So this is just finished, let's hope the data are okay. Right now we are just very preliminary metrics on the networks, and this is the first time that we really see the household network structure coupled with the school network structure. And so we've been doing more and more work in this respect. And finally, when we think of social networks, we think of humans, but animals, they also have social networks, and they've been studied quite a lot. We are collaborating with the University of Exeter, mostly the group of Darren Croft and Robbie McDonald. And we started initially with cats, and it was a terrible idea. It never worked. Basically, this single guy was responsible for derailing our entire experiment. We lost all of the sensors. If somebody's curious, I'll tell you during the coffee break the story, but basically, don't work with cats, they're just too smart. So we went to dogs. Dogs are more well behaved. And in this case, we are working in rural Chad. These are 5 villages in southern rural Chad. And in this case, we are studying rabies. And in particular, we want to relate how the contact network of these dogs relates to the geographical locations of the villages. As you imagine, when you have 2 villages that are close, dogs roam around back and forth. These are sort of collectively owned dogs. These are they're not stray dogs, they're really free-roaming domestic dogs. They have a household they refer to, but they go around wherever they want. And as you imagine, you might have some weak ties between far villages, some strong ties between close villages. So we've been measuring this. In this case, since the geographic span is very large, actually we have our sensors and GPS. So we can actually relate the GPS signal with the sensor signal and calibrate one with the other. And we start having back the data. And you see that, for example, for villages that are, these 2 villages are nearby, the 2 networks exhibit linkage. This village is very remote, so it's pretty much isolated. So this is just to give you a sense of where we are going. And well, I think I will stop here and be happy to take any questions you might have. Thanks for your attention.
So, time for questions? Don't be shy, yes?
Thank you so much for the talk. I was wondering how much does a sensor cost, especially let's say a sensor which you can deploy in this room or in an urban developed place like Hong Kong, as compared to one which needs a lot more well, stuff on it, like the GPS.
Yeah, GPS in a sensor is pretty much a no-go if you want low cost. Not so much because of the cost of the electronics, but because the GPS is quite power hungry. And so if you cannot really afford to use it unless you have a decent battery, or you accept that you're collecting data only for a short time frame. This hasn't been a problem like for the animal social network community, because normally they work with big animals. And I was talking to people, you know, they work with cows and they can stick a 1 kilogram thing on the cow. They literally glue it on the cow, unfortunately, because then the cow is not surviving anyways. And so in this case, you can afford to have a big battery and to collect data. Of course, you know, when you start to go to smaller animals, it becomes challenging. There are also ethical laws. You cannot put on, in a study setting, you cannot put on an animal a sensor that weighs more than 5% of the body mass of the animal itself. And so when you go down to, already to dogs, this becomes constraining. You cannot put there, you know, a heavy battery. Also, you're altering the behavior, right? So to answer about cost, the sensors you're wearing now, they are sub €5 right now, if you could manufacture them. But the reality is that we cannot manufacture them any longer. So we will need to re-engineer things. It's simple re-engineering, but that re-engineering alone will cost probably, you know, like €50,000 to restart the production line. And so it only makes sense if you then are manufacturing, you know, thousands of sensors. So the unit cost is low and can be made arbitrarily low because you can use, you know, economy of scale. But doing this effectively in a study, in a research setting, this is another story. The more complex sensors we are using now, they run in the €20 range for small batches, like hundreds. If you push it to 10,000, like we are now, they go below €10 in a sense. Again, this will change because the cost of the memory is going down, the cost of the processors is going down. But what happens basically is that whenever the cost of a CPU becomes very low, a new CPU with more features will appear, and the old one will be killed, basically. You know, right? There is a market there. Right now we are using a nice product by Nordic Semiconductors. It's the same one that Nike uses for their sensors embedded in the shoes. And they have the radio and the computer in a single chip, which uses a tiny amount of power. One thing I didn't mention is that you're very power constrained in this situation if you want to maintain the lifetime of the device reasonable and the weight of the device reasonably low. So you need to think when you program these devices in very unusual terms. You cannot afford to have an operating system. You have to manage the hardware directly in your code, and you have to do, you know, strange acrobatics. Like, for example, when we switch on the light in your device, you see it's blinking, right? If you keep it on, it will kill the battery in 10 minutes if it's on. So what we do is that we switch it on for a couple of milliseconds. We send the CPU to sleep while the light is on, and then we schedule a wake up after 2 milliseconds, and it wakes up and pushes down and switches off the light. And this way, you know, so you have to do a lot of this, which means you have to have professional software engineers on board. This is a fully distributed real-time system, and debugging is hell because debugging is typically that blinking light, right? So that's you have a 1 pixel screen with the device. It's not true for the most sophisticated. Actually, you can couple them to a computer and you can see. You can inspect the memory of the device as RAM, but debugging is tough, which is the reason why it's important to have these sort of dry runs with hundreds of sensors, because then the corner cases will be tested, and things will fail in mysterious ways, and then you spend months trying to understand why that specific device at that time, you know, what did you see, and that's the way it works.
Just speaking of animals, as you mentioned in the beginning, there are commercial products for surveillance, and I think they are there for animals as well, at least for cows and similar, for accelerometers.
Sure.
So maybe you heard from that before.
Absolutely, absolutely. The thing is that especially for cows, you have all sorts of things, right? That measure also physiological parameters because cows are part of an industrial pipeline. So of course that's highly instrumented. Also for regulatory purposes, you need to be able, you know, if a cow is infected, you need to be able to tell me what happened there. But that's a completely different game and completely different cost than what we do for research. So operating, for example, already with dogs in a rural setting completely changes the game. Nobody cares about that from a business perspective, so there are no products. So the products that are there are too bulky or require infrastructure. The other thing is that cows normally are nearby humans. So you typically can have computers, networks, power. in all of these settings I show you, you have to operate for, weeks without power. We are starting to work on self-power sensors that use like solar light to recharge the battery, or that use vibrations, harvest vibrations to nonlinear devices to actually power up things. I think this will happen in the future. A lot of the IoT stuff will be self-powered, just because the logistic of changing batteries is very bad.
Anja, please.
I was wondering, how much resistance do you get from people or potential subjects, and especially depending on the location or the population that you want to work with?
Yeah, it's a great question. It's very difficult to answer in general, as you imagine, because it depends a lot on what other things you're asking and what type of culture and organization you're in. I'll make you a few examples. Working in hospitals, we soon have to face the difficulty that it is illegal and also highly unpopular, the idea of using this data to monitor performance, presence of staff at the hospital, right? In Italy, it is illegal to measure that through objective means, because you have an official device that you swipe in and out, and that is the reality. And so in this case, we have to engage with unions, tell them, look, we are doing this for scientific purposes. We will not share this data with the hospital managers. I mean, this was the deal, right? And we did not. And then we got everybody on board. We have 92% of participation. But I think that your question is great because it points to the fact that you really need to get yourself deep into that specific community, talk to people, which is why, especially in developing settings, we organize meetings with the people to explain what we are doing and onboard them. In schools, you have different type of problems. You're dealing with minors. So minors cannot express consent. You need to engage the parents, and normally what we do is that we organize a couple of days with the teachers, the school principal and the parents to explain what this is about and onboard them, and then the parents sign the release form for the kids. Different places have different regulations. The reason why I love the upcoming GDPR, even though it places a few more constraints, is that at least it makes one single rule valid across Europe. And so it creates certainty, and people will be more comfortable dealing with that, especially the lawyers. You need to talk to the lawyers, you need to explain what you're doing, and of course they will ask you questions that you don't understand and for which you don't have answers in many cases, right? But the reality is that here we are really working at the interface of our physicality, and so it makes sense that we deal with these problems. Yeah, I mean, it depends.
I have two more questions actually.
Oh, wow.
The first one is you operate in the 2.4 gigahertz spectrum.
Yeah.
So I'm curious about interference with, I don't know, Wi-Fi, for example. Yeah. And my second question is about spatial resolution. Wow. Spatial resolution.
That was interference.
That was interference. Demonstration. And my second question is about if you have these disconnected sensors where you store information. Yeah. You mentioned in Africa you've solved it by having a GPS, so you have spatial resolution as well. But for example, in the case when you bring it into the household where you might not have one of these stations, do you have any way of still getting spatial resolution?
So let me start from the second question. We do not use a GPS. Actually, we do not want to use a GPS unless we are in a pilot situation where we are calibrating the signal. The entire point, the entire philosophy of what we are doing is to measure proximity without going to position, right? So that means that you need to learn how the signal damps out, and that's going to control your resolution. What we do in the new devices is that we measure the receive power and we threshold that. So we can actually change the definition of proximity when we analyze the data. What we are doing in the devices you are wearing now is actually that we are looping over 3-4 preset levels of power, and then if we receive, we use the power level at which it was transmitted as a proxy for the proximity bubble. So long story short, normally we don't have position information. Normally we only have, if you have antennas, you can use that as a position proxy. If you are in a fully distributed setting, there is simply no positional information, but as I showed you in the hospital, you can still put sensors, static sensors, in rooms, on objects, and proximity to those becomes your location awareness, in a sense, right? Well, you measure it as a proxy. I could stick a couple of chip sensors in this room. The cool thing about the sensors is that they can afford to only transmit. And if they only transmit, they can go on for a year on a single battery. And it's counterintuitive, but what sucks energy in these devices is receiving, is not transmitting. Because while you receive, you need to have a chip that's listening and saying, is something arriving, is something arriving, is something arriving, literally looping over this like many times, like per millisecond, right? So this costs energy. The reason I could go into the detail there if you're interested, but long story short, there is no positional information unless you think about that. Interference, it's real, because we are using a crowded spectrum. So what we do typically when we measure things is that we go in and we measure the spectrum in that band, and then within that band we can choose, we have a freedom to choose a channel. And so if we see that, for example, if we know that the Wi-Fi is operating on specific channels, we just stay away from that. There is no collision detection mechanisms in this radio, so if you have interference, it's really destructive. You will never receive the signal in the first place. You will never know it was damaged.
All right, and with this, let's thank Ciro again, and